So I will start with talking about Krylov solvers and why they're used, and then we have a small hands-on during that time. Before I go to multigrid methods, and we'll say a few words about algebraic multigrid software that's out there. Then I will more focus on the hypre library because I'm one of the developers of that library, and we will have both multigrid methods as well as Krylov solvers. So I will say a few words about their interfaces, and then we'll talk about how does multigrid work and talk about two specific multigrid solvers, and unstructured and structured multigrid solvers in hypre. And we will do some more hand-ons for the specific solvers. Okay, so iterative solvers. So we want to solve a linear system, AX equals B, and A is a very large sparse matrix of size n, because now we're talking about n could be billions. And generally, of course, we don't really want to use a direct solver because, for example, Gaussian elimination would be way too expensive because you get a fill-in and you suddenly have n square non-zeros or whatever you have to deal with. And so that's one of the reasons why I really want to look into iterative solvers. One very simple iterative solver here is Richardson's iteration. You see here, you just have your approximation xn plus 1 of your solution of the linear system up there, and you just add to it the residual b minus axn to hopefully get a solution. If we actually look at the corresponding error equation underneath, it shows you that we would have I minus A, and so unless A is a very nice matrix, this probably won't converge because your error might increase instead of decreasing. So what you really want is you want your matrix I minus A, where I is the identity matrix. You want this to be a nice matrix that actually guarantees that you get towards a solution. And so generally, we will try to use a preconditioner. I know we've mentioned preconditioners before. And ideally, such a preconditioner would want to be an approximation of the inverse of the matrix A. And so you would pre-multiply your residual here, or your equation with B, as you can see here in this example. And your new iterative method becomes xn plus b times the residual. And your error equation down there would be I minus BA. So if your preconditioner is very good, then you will actually get a good convergence. So of course, we are looking all this in terms of a parallel computing, exascale. So you want to have a preconditioner that is parallelized as well. And some simple ones here would be Jacobi, which is just the inverse of the diagonal of the matrix A, which I think probably most people might be familiar with this, or the Richardson method up there, which correctly actually contains a parameter lambda, which for the example above, I just chose lambda to be 1. But of course, these are very simple preconditioners, and in itself, generally, unless you have a very diagonal dominant matrix, will not converge very well. And so we will probably look for some better ways to find an iterative solver than this one. Okay, so let's, here's the equation again. Let's take a look at that iteration here. So if you look at xn plus 1 and you start with x0 and start applying this several time steps, you will, several steps, you will actually see that this actually boils down as a linear combination of these vectors, ba to the power of I times bb. So you have these polynomials of the matrices ba times the vector bb in this case. And so your approximation essentially is in this space that's generated by these polynomials, and that's what we call a Krylov space. So if you want to have a really good solution in this space, you wanted to achieve this by optimizing the following norm, b times ax to n plus 1 minus the right-hand side, over that square. And so to get the very best alpha I you can get, to get something that's close to your solution. And since the Krylov space, these vectors that have these polynomials in general are not very good vectors to use as a basis for this because they are not that robust, you want to have an orthonormal basis of this. And so the idea is construct a new basis for this Krylov space, but orthonormalize those vectors to have something that's more robust and works much better for you. So in this case. And that's essentially what happens in the generalized minimal residual matrix. You will actually take your Krylov vector, each one you get a new one, you actually try to orthonize it in the spaces. And we actually call these QI also search directions. This is usually done with some kind of QR factorization. There are different versions of GMRES and so on. And that's basically the idea behind GMRES. I'm not giving you the algorithm here because I just wanted to give you the simple idea. So if we actually look at GMRES, it consists of fairly simple operations, something we would like to see, especially when we are running in parallel. We want to make sure we have some operations that can be easily used there. So there are various inner products and norms that have to be used. There are vector updates which are really parallel. And then, of course, there is a matrix vector operation in each iteration, which requires just nearest neighbor updates, well, depending, obviously, on your actual matrix. And you generally want to have a preconditioner, which can be complicated. We'll see this in the section after this when we actually look at multigrid. GMRES, now, of course, if you would just keep building your space, and you might have many iterations, this can become very complicated. You don't want to have hundreds of these search directions. So GMRES is generally used in a restarted form here. So after k iterations, you kind of throw out your QIs and just restart again, but use your latest approximation. And so hopefully get closer to the solution. And in the whole context of parallelization, there are all kinds of ways to try to reduce, especially we don't really like too much the global reductions which perform across a whole parallel machine. And so there have been all kinds of efforts to try to reduce or overlap the communication, reorder things to make sure that you actually can have as little communication as possible, or you can overlap it in different ways. And there's versions like pipeline GMRES, which I believe are also in PETSI, has some pipeline GMRES as well. So GMRES, of course, is not the only Krylov solver out there. There are actually a whole slew of Krylov solvers out there. I will only mention pretty much two more. One, the oldest Krylov solver is actually conjugate gradient, and maybe you all have heard of that one. This is specific for symmetric positive definite matrices. It also tries to orthogonalize something, but GMRES actually doesn't do it over the 2 norm. It does do it over the energy norm, which is the square root of x transpose AX, which is a norm because A is symmetric positive definite. And conjugate gradient has the additional nice property that it actually uses a 3-term concurrent recurrence. That should be recurrence. But it does. So you don't have the problem with this buildup of the space of all these. You only need 2 more vectors, which is nice. So you only need 2 inner products and a norm per iteration. So 1 iteration is certainly generally much cheaper than GMRES. So if you can use conjugate gradient, that's probably the better way to go, but you need a symmetric positive definite matrix. Now, because conjugate gradient has these nice conditions, when people wanted to solve non-symmetric problems, they were looking at different options, and GMRES was one of them, which keeps this orthogonality property in a way. But they also would have liked to keep the 3-term recurrence. And so what happened then was that they actually invented another one, which originally was BiCG, which essentially used the Krylov space on A and A transpose. So we had these 2. But because using the transpose of A is bad, there were others developed. And so the one that's actually also often used is called BiCG stab, which also uses the 3-term recurrence. Because you have these 2 different Krylov spaces implicitly underneath, I mean, essentially, you actually have 1 BiCG step iteration is more the cost of 1 conjugate gradient iteration, because you have these bigger polynomials that they're working with. And so they are not really equivalent. Instead, you have 2 metvecs as well as 2 preconditioning applications and as well. BiCG stab, when it works great, but it does have a more erratic convergence than GMRES. GMRES tends to be more robust. So depending on what you do, if you have a very good preconditioner, it probably doesn't matter so much. If it doesn't take that many iterations, GMRES might just be fine. But they're both useful methods. Okay. So now let's go to our first hands-on here. you can actually just click on this, and it should get you right there. So you see here, when you get to this page, you get here to this page, which gives you some at a glance. And then let's go to the first problem we solved. We actually just go to a simple Poisson equation here with Dirichlet boundary conditions that uses a disk grid with central finite differences. Laurie talked about them this morning already. If you want to begin the lesson, please go to the Krylov _AMG directory on here, which I am here. You can see here already. And if you want to open the answer form, you can click on that here to get to our questions to answer them. But before this, let's just go here. Essentially, when you actually go to the Krylov one, and you see there are essentially two executables. We're going to first, for this part, we only use the IJ executable, okay? So if you want to see what kind of options you have to use it, you can say .ij-help, but you don't have to do this right now because I have the important ones are here already. So let's just look at them here. So you can choose your problem here. The default is just a 7-point, it's just the Poisson equation, as I said before. The different solvers for right now, we're only interested in GMRES, PCG, and by CG step up there. And you can set the Krylov subspace size with a -k. The default is just 10, so that's what we're going to start with. The default size for the problem is actually 30 by 30 by 30. And this -n tells you the size per process. And then you can set the process topology, which we're going to do later. Right now, we first just run it on one process, so this won't matter. You can set the topology later with capital P. The tolerance for the problem we're running is 10 to the -8. So let's just run the first one. Try to do this. Okay, you can just, or you can just type it in, .ij-GMRES. Since the default is, so you see here, this essentially runs very nicely. It does take you about 392 iterations over here. And you see the time, and down here it also shows you the actual residual norm, which is smaller than 10 to the -8. So this converged, but it took 392 iterations. Okay. Okay. So, and there are some questions here. So what we want to do next is we want to increase the size of the Krylov space to see what actually happens. So you can run the same thing again and just set the square to 40 and see what happens to the number of iterations as well as its time. And then run it again with 75 and see what happens to the time and the number of iterations, so you can see. And then you can try to answer this question. Once you're done with this, you can also try to see what happens if you actually run CG on this. So replace -GMRES by -PCG and see what happens now. We actually see that this goes much faster, which is not very surprising because we know that one iterative step of the conjugate gradient is much cheaper than GMRES. But it also converts really well. Now, this is a metric positive definite problem, so you would imagine this should work really well. And let's try to do the same thing with by CG step. We see here, actually, it does take less iterations than PCG, but it is apparently slower. So you can think about what we said earlier about the actual how one iterative step of by CG step is composed, and that might give you the answer why it's actually slower. So let's go now, and I just wanted to do a few parallel runs. So the way you run it in parallel, actually, here, obviously this is the first one to run it here. That was just running one. All right, and now let's just run the same thing using actually 8 processes. Remember that the size is just per process. So if we have a 50 by 50 by 50 and we run it on 8 processes, then we get something that's 100 by 100 by 100. And see what happens. The number of iteration more than doubled about, and the time went up quite a bit. So yeah, what's the question?
Why did the number of iterations increase?
For a conjugate grade, you mean in this case?
Yeah.
it's a bigger problem, right? So the problem is 8 times as big. And conjugate gradient, actually, the number of iterations will increase when you actually increase the problem size. So that's actually when I keep going here in my talk.
Well, even with keeping the same size grid, just changing from 1 process to 8 processes.
Yeah. No, we did not. Remember, the size was per process. So we increased the problem size by a factor of 8, actually, when we use 8 processes. So, yeah. Otherwise, the number of iterations should have been the same. So, yeah, that's a good question. So, okay. So, essentially, what happens when you have a conjugate gradient, you saw that the number of iterations went up, the time went up, and so you end up with something like here, diagonally scaled conjugate gradient is unscalable. We wanted to scale this up to millions of cores, right, or processes. And so this is not good. So we want to have a preconditioner that prevents that, that's scalable. And that's where multigrid methods come in, because they are actually theoretical optimal, meaning they solve a problem of size n in about O of n operations when they're well constructed. There's various multigrid software available out there. Therefore, for example, there's ML or MuLu, which is a part of Trilinos, which uses some smooth aggregation type algebraic multigrid. PETSI has a geometric GAMG, which is kind of a mixture of geometric and algebraic multigrid, use geometric on higher levels and algebraic multigrid underneath. But PETSI also provides access to ML as well as through some of hypre's multigrid solvers. So you can get a lot through PETSI. And then, of course, there's hypre, which I represent here. And we have quite a few different algebraic multigrid solvers, including some for special problems, such as Maxwell, or we have some new ones for specifically non-symmetric problems, and so on. And all of these are helpful. All these software are really good software that really helps to give you good performance. So let me say a few things about hypre. Hypre's specialty is A, it provides multigrid solvers, but B, it also has special interfaces. We call them the conceptual interfaces because we want the users to be able to look at a problem through the way they look through it. For example, when you have a structured grid like you have up here there, then you want to be able to look at your system in a structured and stencil, use a grid and a stencil, for example. Or you might have an adaptive match refinement grid or a block structured grid. Then you should be able to construct your matrix through that. And finally, or we also have finite elements as well, or just the general linear algebraic multigrid interface, which most of linear solvers library have. And underneath, we do have different solvers that can be used through these. Now, if you want to use take advantage of the grid and stencil format, we have PFMG here, which is probably our fastest multigrid solver. But our most used is AMG, our unstructured algebraic multigrid solver, which can be used through this. But it actually can be used through all these interfaces, which is nice. But of course, it's more expensive than if you actually, at this point, then it would be more efficient to try to use PFMG. And below this, we do have different data structures depending on the type of information that was provided through the way you looked at your matrix. So why would we do this? For once, it gives a natural view of the linear system. And then also, we wanted to help to make it easier for our users to be able to, if they have a certain way of looking at it, then they can just implement their problem using that interface, and we do the work underneath to turn this into a matrix with rows and columns. The most important part, of course, is that it allows you to get more efficient linear solvers by being able to take advantage of the additional information that you might get. So there are essentially 3 interfaces in hypre. There's a structured grid interface with logically rectangular grids. There's a semi-structured grid interface, our most complicated one, which allows you to do all kinds of different things, as I said before, block structured grids, et cetera, but it also allows you to do finite elements, actually. And there's finally our linear algebraic interface, which just if you have a matrix vector in some kind of, uses some kind of compressed sparse row type data structure underneath. So hypre can be used, our multigrid solvers can be used in all kinds of different applications. So here you just get some of them are listed here. And generally, it does give very good weak scalability on BGQ type architecture. So here was a rundown on Sequoia using a 1.125 million MPI task and different combinations of MPI versus OpenMP here. And for this black round, the best one actually, we did also use 4 OpenMP threads underneath. So you had actually about a 4.5 million parallelization going on here. And you see you get actually very nice scalability. So let me tell you, how does multigrid actually work? So you essentially have, you start with, if you have a simple smoother like Jacobi or Gauss-Seidel, you start with an arrow on a fine grid, and as you smooth it, after very quickly, after a few iterations only, you are able to get rid of the large arrows very quickly. But the small ones will take a long time. And so to make this all faster, after a few iterations with a smoother, you actually go to a coarser grid, and there you approximate your arrow on here and continue this whole procedure, and you keep going all the way down. And in that way, very quickly, you can smooth out the actually small errors. And you then interpolate up by using a suitable interpolation to make sure you actually correctly interpolate your error. And so you'll be able to very quickly, in such a V cycle, as we call this, to reduce your errors. Algebraic multigrid, now this is this general idea for a multigrid method. Algebraic multigrid, of course, is different in that it generally just uses the original matrix, so you don't have to build grids in between here. And so you essentially just have to give it your linear system, and it should perform all this for you. Is there a question?
Could you be more specific what you mean? You don't need a grid? That seems a bit confusing.
Yeah, because you just essentially need a matrix. It's a black box method, okay? So, I mean, of course, your problem originally will probably have been generated on a grid, right? But then you have a matrix, and so you can just give it the matrix.
Okay. Like
you see what I mean? Yeah. Yeah, so for geometric multigrid, you usually have to generate your grids on each level, and it will do. But for algebraic, you just essentially put your matrix right-hand side into the solver, and it will do all the things underneath for you. You know, so that's a difference. So there's essentially the AMG building blocks. Essentially, you have the setup phase in which you sort of select the coarse grids. As I said, they're not really grids. So you just pick the variables that you want to take to the next level, or you aggregate. Like in smooth aggregation, you actually aggregate your variables to different ones, so you know. But in the ones, Boomer AMG, you actually pick the next variables for the next level. You define an interpolation. And essentially, you do this by generating the graph of the matrix, you know. So what's your question?
Says, how exactly do you define your interpolation?
It's some heuristics you use, where you're trying to essentially approximate the error by using, you know, AX equal approximately 0, and so you're trying to, yeah.
Linear interpolation, or?
I'm sorry.
So linear interpolation?
Well, yeah, there are different types. So some of them might be constant, you know, or linear, depending how good you choose it. So it's not really like polynomial interpolation, if that's what you kind of have in mind. It's really based on heuristics. If you're thinking about the algebraic error, AE, you want it to be approximately 0, and based on that, you choose your interpolation. And there are different types. And just know that you can generally only use the points around you, you know, your nearest neighbor to do that. So. And then your restriction often will just be the transpose of interpolation, because often you have a symmetric positive definite problem, and then that makes sense. But it does also work for non-symmetric problems quite often, unless they get too difficult. And the coarse grid operator is just you just multiply those 3 matrices together, and that's where you really don't need the grids anymore, and that might answer your question where, you know, there are no more grids. There's just a new matrix you have, and then you just repeat the process down. We call this thing a Galerkin product, so although there are also non-Galerkin sort of options. And then the solve phase is just the V cycle I showed you earlier, where you do a relaxation here. You're smoother. It can be Jacobi, Gauss-Seidel, but obviously, since we do parallel, we don't really like Gauss-Seidel that much. It's highly sequential, or you would do some kind of block Gauss-Seidel, where you just do Gauss-Seidel within a block, but use Jacobi to do it across, or you do some polynomial smoother. And then the rest is just sort of, in a way, matrix vector multiplication in a lot of ways. So it's very nice and straightforward. And when you solve your error equation, you just, this is just a 2-grid sketch strategy. Obviously, you will do the same process when you go further down.
So it always starts in V cycle, it doesn't do any other cycle?
You can do other cycles. We only look at the V cycle here, but if you want to do hypre, you can do a W cycle in hypre. Now, in the context of parallel processing, a W cycle is kind of very expensive, and for various reasons, which you just see, because you end up spending a lot of time on the lower levels, which it's not very efficient, and there are some extra reasons why that's not good, which you'll see after the slide. As I said before, our most used multigrid solver in hypre is Boomer AMG. It's unstructured. It's based on unstructured grids, really. You have an IJ interface here. And it's originally, you have all kinds of knobs on there, although I think we have put some defaults in there by now that are generally fairly reasonable for a lot of problems. But if you add some extra stuff, you might be able to get some better performance in some of cases. Just depends. And it can also be used through PETSI as well as Trilinos. OK, so one of the issues which will just answer maybe part of your question too, is because we are generating this operator RAP by multiplying these 3 matrices, you can end up getting some nasty behavior. You can get really some ugly stencil growth. Essentially, the number of non-zeros really grows when you increase your, when you go to the coarser levels. And here you see actually a communication pattern, what happens. Here you have 128 senders and receivers, so you see wherever there's color, there are messages being sent. And this is actually not the first level. This was just even the 7-point Laplace problem, so this was starting at a later level. You see how it starts spreading out, your communication across, and things getting worse. Over here, you start actually seeing some processes dropping out, because when you have less variables available, then not all processes will have information anymore. And so this can be a real problem, because it can really slow down performance. So if you have your W cycle, you might end up spending a lot of time in this area, which you really don't want to, you know. So. OK, and so one thing that's also important is to look at something called operator complexities, because of these growths that we see, which is the number of non-zeros of all the operators AI we generate on each level divided by the number of non-zeros of the original one. Because if that's big, that affects the number of operations as well as your memory usage. And so what you would like to have something that's smaller than 2. You can't always get that, but if you can, that's often very good. And you can control this in various ways. One thing we will look at here you will see, is to use more aggressive coarsening, like, for example, coarsen twice and then just have a longer range interpolation. And that will actually can really reduce that operator complexity and that stencil growth. So, and there are other things. You can truncate your interpolation. You also can use a non-Galerking approach, which sparsifies your operator A. But you have to be very careful with this, because if you do too much of that, then your conversions gets too bad and you don't win anymore. So. Underneath, it uses a CSR data structure here, which is essentially compressed sparse matrix. So it consists of 2 CSR matrices, which compresses these, where the red parts here is essentially, if this is the number of processes, so it's distributed row-wise, are just point to the local coefficients, and then the other ones are 2 off-processor connections. And you do need a map, because we compress this part also, we do need to map between local and global column indices. And so there's a lot of indirect addressing going on, which costs time. You have to do integer computations and so on. Can get quite complicated. So now let's talk about the structured solvers here. We do have several. There's SMG and PFMG, particularly under the structured interface. SMG is very robust, but it's also very expensive. It uses plane smoothing. And so a lot of times, AMG can solve the problems and is actually even faster than SMG. But there are problems which actually AMG doesn't solve, but SMG does solve them. So the one that I really want to focus on here is PFMG, which uses simple pointwise smoothing and is less robust than SMG, but it is really highly efficient. The nice thing about PFMG is that the stencil growth is limited, so you don't have this mega thing we just saw for AMG, and there are also constant coefficient versions. So the reason, let me just say a bit about PFMG so you understand why the stencil stone grows. So here assume for the structured interface defines the matrix in terms of grids and stencils. So that's a little contradiction to what I said earlier. So yes, we do have a grid at the beginning here in this, for this one. So, you know, but only on the first level when you put it in, you just define your matrix in terms of a grid and a stencil. So here, generally this came from PF as a par flow because originally the solver was used for subsurface problems. In a context, and they were using some finite volume schemes with central points here. So that's why we look at the grid here in this way, actually. So what you do, essentially, you use semicoarsening. PFMG does use semicoarsening underneath, so the next grid in the direction of an anisotropy. So it works actually really well for grid-aligned anisotropies, different from other. So it would give you something like this, and then just interpolate from these 2 points next to it. And the nice thing about this is since it does use 2-point interpolation, your stencil will not grow beyond 9 points in 2D or 27 points in 3D. So you don't have the big major growth we saw. There is actually also a non-Galerkian approach, which does use some geometric knowledge and thus preserve the stencil size. So if you have a 7-point stencil, it stays 7-point actually. But that, again, this doesn't always work. I mean, obviously, this one works generally better from a mathematical point of view, but this one is more efficient when it works. And it uses a pointwise smoother, and it is our most efficient solver if you have a problem that's useful. Obviously, if you have a complicated domain or whatever, you want to use BoomerMG because this won't work. So just a few words about, again, this is a structured grid interface, uses your grid, which you define in terms of boxes, a collection of boxes, and you have a stencil, which is obviously it can be variable coefficients, even so we just have a constant stencil here. And the underneath matrix data structure uses a stencil. It uses grid boxes here. In this case, you have defined them. This is a very simple example of just 2. And then it uses a data space which includes the ghost layers for these. So you have the information of your neighbors right here, which makes it actually very efficient. And the ghost layers here is also within a process. So it's not meant in terms of parallel processing. And then your stencil entries, I mean, the data are stored in terms of for each individual stencil entry and for each box in the following way. You have this, this, this. So the nice thing about this is it's like a diagonal storage, which is for the computer scientists here, they probably know that's a very efficient data storage scheme. And for GPUs, it's sort of the one that you really would like to have. OK. So having said all this about these different multigrid solvers we have here, generally you would like to use them in combination with conjugate gradient or GMRES or by CGSTAB, as a matter of fact. And you can get additional performance improvements because these type of methods really help each other. So let me just give you one more example so you actually see something about the performance with these different solvers here. This was for a subsurface problem, which has various, for this diffusion problem here, where kappa has jumps of the order of magnitude. Here's like a picture of that. And you see here different solvers. These were all preconditioned, multigrid preconditioned conjugate gradient. Here's just diagonally scaled. The purple line is diagonally scaled conjugate gradient. We scaled this is a weak scaling study, scaled up to 32K cores. And the different colors you see here up here is black is use the BoomerMG with PCG using just the default vectors. And down here you have PFMG just using the default vectors. And you see this is actually much faster. Here we used some additional knobs on AMG to see you can actually, for this problem, we are able to improve this quite a bit by using some aggressive coarsening and some non-Galerkian approach. And down here is the PFMG using the non-Galerkin approach I mentioned, so you get an additional improvement. So you see there can be quite a difference if you are able to take advantage of structure.
What do you get from, I mean, I'm trying to understand that algebraic multigrid is used as a preconditioner for the iterative methods.
Yeah.
So what do you get from algebraic multigrid that we use as a preconditioner?
What do we get is because, remember, the preconditioner, we want it to be an approximation of the inverse of A. So in a way, you're doing that here. You're approximating. AMG is a standalone solver also, you know, so it does give you a really good approximation already of this sort of inverse problem. And when you put it in there, you know, so you get much closer. Your condition number, you could say, is actually much better now than before if you want to look in terms of that. So. And we're going to run some AMG problems now for the problems we just were looking at, again, to see what actually happens. So let's just try to run this here, AMG here, just AMG as standalone solver. So for this, we actually end up just needing 12 iterations compared to 100 whatever we had before. But the time, actually, if you compare the times, you might notice this is actually slower than CG was for this problem. This is not a small, this is a pretty small problem, so, and it does take some work. Setting up the preconditioner is expensive and so on. Now let's just try to run the 8 process code. Again, you can do this. This is, again, AMG standalone. We did get an increase in number of iterations, almost doubled also, but now the time is actually better than when we are in CG before. And if we now combine this also with CG, maybe there are too many of you on a login node. Generally, this is actually faster. Oh, it just finished? OK. Yes, it shouldn't take that long. So that is, you saw, but however, it took only 11 iterations, so it was much faster, and it also would have given you less time. Now, let's take a look at the operator complexities for that. So let's take a look at that here. First of all, let's take a look at the stencil. You see here the operator matrix. You see here we're using up to 8 levels for this problem, and we actually, this shows you the average number of non-zeros per row, and you see it grows up to 91.1. We even get one of 183, the maximal size, from 7, so that's pretty bad. If you actually look at the operator complexities down here, whoops, here you see it went up to 3.2, and as I told you earlier, you want them to be smaller than a different number than this. So this is not as good as we really would like it to be. So what do? We actually try to run this if we're able to, and this will be a little cheaper, so because we're using less memory now, and hopefully this will actually come. See, it worked really well now. And if we look at this now, then you actually see that the number of here has decreased. It's still, you still have some that are pretty big, but overall it looks much better. And you also see that your operator complexity is much lower. It's kind of where we would like it to be. So the number of iteration has increased, but the overall time is much better now, actually. So I wanted to show you also what happens if we run our structured solvers. And for that one, we actually do have, before this, you can just run it and see what happens if you actually use 2 levels. Can do that too here quickly. And what you see here, the number of iteration goes up when you run 2 levels, but the time is actually worse again. So you want to be careful with doing it too aggressive because you might end up not winning on this. But I also wanted to run the structured solvers here. So for this problem. So let's just run the structured solver. For this, we have to use the struct executable. And now we just want to run PFMG. And yeah, I think the rest doesn't really make too much sense. That doesn't work here. I'll just run that and see what happens. It takes 35 iterations, so it takes more iterations than AMG did before, but the time is actually faster. So let's combine it now with PCG. To see we can get additional improvements. The number of iterations goes down, and we get better time now. And let's also add get the non-Galerkin approach, you add -RAP1. And if you do that, the number of iteration actually stays the same, but you get an additional time improvement. So
I'm just confused about using the multigrid as a preconditioner.
Yeah.
For me, preconditioners it's just an additional matrix you put in front of your matrix to make the problem easier.
How you do this? Yes, essentially you imagine, because what you're trying to do, you try to get an approximation of A inverse. But that's sort of the same as trying to solve a system, right? Yeah, and so essentially you just put it into your Krylov solver and the preconditioning step and essentially try to approximate, you know, and that's essentially that. So, yeah. Okay. Is there any more questions?
There's one there.
Oh, okay.
Since you're using it as a preconditioner, do you not solve it exactly? Do you have like some tolerance that you?
Yeah, we only use one iteration of it actually, so it's just, yeah, generally.